my dad was like, I'm not taking off of work.
Everyone doing okay on Friday? Friday the 13th? This is the second Friday the 13th this year again? Yeah. I don't think there's been one since March. I'm going to go over 2 of the questions from the homework. I'm going to kind of go through them pretty quickly. But questions 47 and 63, I believe, those were the 2 that were asked multiple times. I'm going to go through those. If you did have other questions and you have on the homework form, please look at the comments that I make on your homework. So anytime that you complete a homework assignment, I do leave comments on it. And I don't know if some of you receive those and some others don't. I guess it depends on what notifications you have on. Any homework assignment that I look at, which is every single day, I look at every homework assignment. I do leave comments and like suggestions about how to correct your mistakes that you made. So please look at those comments because I can't always go over every single homework problem that people have questions on. There's just not enough time. But check the homework because I do have comments. So in it, if anything, like you receive more feedback on your homework from me now because of the virtual aspect than you would in a regular year. Because a regular year, I'm glancing at your homework as I'm walking by in class. Where now I'm like looking at every single homework assignment, every problem you complete. So we're going to look at rational functions today, Monday and Tuesday. So this last little part of chapter 2 is the rational function. We're going to be finding those asymptotes of the rational function. So the graph, those imaginary lines that the graph is approaching. We're going to look at those today as well. And then you have some book problems that, like today is more analyzing a function and not graphing. So we really won't focus on the graphing until Monday and Tuesday. So this is like the analyzing part, trying to get all the pieces together. And then Monday and Tuesday, we'll try and see if we can pull those pieces together and actually graph. And I think 11 to 17 is like matching because like you're given a graph, can you match it with the function based off of what you know with the asymptote? So we're going to start with 47 because that was the first one that I saw. That was kind of suggested to go over. So if you want to find 47 on your homework, this says to find a polynomial function with real numbers, or I'm sorry, real coefficients that have the given zeros. And in 47, we have the 0 at 2 and 2, and then another 0 at 4 minus I. So Grant, what would the degree of this polynomial be if we have a 0 at 2, 2, 4 minus I?
Would it be 3 or 4?
Why would it be 4?
Because 4 minus I is also 4 plus I.
Yeah, nice. So remember, conjugates, complex conjugates occur in pairs. You can't have one without the other. So if they give you a 4 minus I, the other one is 4 plus I. We're going to write these as factors. So you can write the x minus 2, x equals 2 becomes x minus 2. You can write it twice or you can square it, either way. And then if x is equal to 4 minus I, when I make it a factor, I have to take the 4 to the other side. So that becomes x minus 4. And then I have to take the I to the other side, so that becomes plus I. A factor must have an x. Otherwise, it's not a factor. It's a 0. It has to have an x with it to have a factor. The other factor was 4 plus I, or the other 0 was 4 plus I that Grant gave us. So again, if I take the 4 next to the x, and then I take the I next to the x, I have to subtract that one as well. So that's what it would look like in factored form. We're going to multiply this to try and find the polynomial. When you multiply it, you want to group the real part of that expression together. So I'm going to take the x because the x is a real variable and the minus 4 because that's real as well. I'm going to think about those as being 2 terms that are combined together. Same thing over here. So So when I go to FOIL this, I'm foiling x minus 4 with x minus 4. Which again, I can write it as x minus 4 times x minus 4. Or I can write it squared, however you want to write that. But that would be my first term. My outer term and my inner term cancel because they're conjugates. I'm not going to write them down because they will cancel every single time if you have conjugates, which I do because I have a plus and a minus. And then my last terms will be an I and a negative I, so that's a negative I squared. So I'm going to just do this back part first. So Jeremy, x minus 4 times x minus 4 becomes and then negative I squared is really, yeah, so I squared is negative 1, so that means I'm adding 1. So this gives me x squared minus 8x and then plus 17. So that's the expression I get from multiplying the two factors that were imaginary together. I also have x minus 2. I'm going to just bring it down. X minus 2 squared becomes x squared minus 4x and then plus 4. That goes back in parentheses as well. So now I have two factors that are trinomials. How the heck would you multiply those together? Like I have x squared minus 4x minus 4. I have to multiply that with x squared minus 8x plus 17. How do you do that? 30?
You just divide each, or multiply, I guess, like distribute each of your numbers into the other equations. Like x squared would go into all three, and then negative 4x would go into all three, and then 4 would go into all three.
Perfect. So she said distribute, and that's a great word. So you're taking the first term, distributing it to everything in the back. So this is going to be a really big problem. So distribute x squared in the front with the x squared, with the 8x, negative 8x, and then with the 17. So then I distribute the negative 4, like each piece gets distributed. So then we have the negative 4x with the x squared, negative 4x with the 8x, and then negative 4x with the 17. Let's see, 4 and 17. 58? 68. 68? Okay, and then one more time, I'm taking the last 4 with the x, and I ran out of room, so I'll just write it underneath here. That 4 with the negative 8x, and then that 4 with the 17.
Shouldn't it be a minus 68x and then 4x squared?
This guy right here. Yep. Thanks. So it's huge. There should be 9 terms because I'm taking 3 things and multiplying it by 3 more things. That's why it's a really big expression. So when you're multiplying expressions, if I multiply 2 terms by 2 terms, I get 4. Well, if I multiply 3 terms by 3 terms, I end up with 9 terms. So when you combine your like terms, I see an x to the 4th that's all by itself. It looks like I have 2 terms that are x cubed. Lots of x squared terms. So 17x squared, 32x squared, minus 4x squared. Grant, what did you get when you combined all of them together?
53.
53. All right, and then my x terms are nice, they're right next to each other. Grant, what do you get when you have those?
100.
Yep, I gotcha. And then that last one would be 68. So a lot of multiplying there. Like easy to make a mistake because you're forgetting an x, you're missing a negative, so it's really easy to make just a little mistake there. Question. 104x, there's a negative 68x, so negative 4x and the 17, And then there's a negative 32 with the 4 and the negative 8. Oh, is it 100? I thought you said 104, but maybe it's 102. Sorry. Thanks. Any questions on that? Okay, so this was 47. Number 63 was the other one that there were questions with, and I think they were questions probably because of the foiling the two zeros together. So this was the problem that said, here is a 0, find the other zeros. So Hannah, if I have 1 minus the root 3 times I, my other 0 would be?
1 plus square root 3 times.
Yeah. So again, if I make them as factors, I can then try and find the original equation that would have been created with them. So I have to subtract the 1 and add, I'm going to place the square root in front, or the I in front of the square root. And then the other one, I have to subtract the 1 and then subtract the I root 3. So make them as factors. Group the real variable and number together, and then multiply. So Darby, if I have x minus 1 times x minus 1, what would that become?
It would be x squared minus 2x plus 1.
Yeah. My inner and outer terms cancel, they're conjugates. And then I'm taking I root 3 and negative I root 3. That's going to be negative I squared. And then Darby, what is the square root of 3 times the square root of 3?
It would be the square root of 9, which is also just 3.
Yeah, she said it's the square root of 9, or it's just 3. So when I combine these together, I squared is negative 1. The square root of 9 becomes a 3, so I'm adding 3. So that should be a negative 3 plus the negative sign that's already there. So this is the expression that you have from those two zeros. And then once you get this expression, you're dividing it with the original function. So maybe it was this part here, foiling them together. I'm going to try and write my original function next to it. So I have 3x cubed, negative 4x squared, beats x, and 8. So Brenna, I have an x squared. I want to make it a 3x cubed. I will multiply it by 3x. A 3x. And when I multiply, we get 3x cubed, 6x squared, 12x. And then this is a plus, and that's a minus. So I end up with a 2x, and it looks like a minus 4. And then Brenna, I have a 2x squared. I'm going to multiply it by x squared to make 2x squared, so we would have a 2. Yeah. So then I have 2x squared minus 4x and plus 8. So if you didn't get a remainder of 0, though, there, maybe it was because you didn't kind of distribute this minus sign through. That would be the mistake that I was seeing, just making sure that when you are using long division, you're subtracting all of those terms. So it has to kind of divide through or distribute through everything there. So your remaining 0 that we were missing should be negative 2/3. Along with the original imaginary numbers of 1 minus root 3i and 1 plus root 3. So again, I'm going to look over that homework, give you some thorough comments back, probably paragraph work. Usually I kind of go question by question, but look at those assignments and check out those posts so that you can kind of see that feedback that you're getting. Questions? So today we are going to talk about the rational function. If you have your calculator, if you could pull that out. We will use the calculator just to kind of refer to when we're looking at a graph. to remind us about asymptotes, where they may be located, what's going on with the picture. So this is section 2.6. We're just looking at the rational function and trying to kind of analyze it today. Monday and Tuesday we'll be graphing them. So we'll just kind of look at the calculator as a little bit of reference to kind of decide what's going on with those asymptotes first. So we've been working with rational numbers. The rational zero test is P over Q. By definition, a rational function is P of X over Q of X. So all that means is that you have two polynomials that are being divided with each other. That's what makes a rational function. That's why we learn rational functions and polynomials together in the same chapter in this class. Because two polynomials create a rational function. So one polynomial divided by another one. A couple of pieces of information besides the fact that there's two polynomials. It says Q of X isn't 0 because I can't divide by 0. So the denominator's function cannot be 0. And then it also says that P of X and Q of X have no common factors. So that means I wouldn't be able to divide or cancel out something from the numerator and the denominator. They're not going to have anything in common. So they're going to be two totally different polynomials that have no relationship to each other to create this rational function. So to give us a little review here, we haven't done domain all chapter. We did it in chapter P and we did it in chapter 1, but we really haven't looked at domain in a while. So when you're finding the domain of a rational function, what do you look at to get the domain of a function when you have a fraction? Evan, do you remember how do I find domain? No.
I would look at the denominator because, like, for example, that one, it can't be less than equal to 0 as in the square root. Oh, no, because it's in the denominator.
Yeah, because it's in the denominator. So again, going up to the definition up here, the characteristics of the function, Q of X can't be 0 because we're not allowed to divide by 0. So to help us find the domain, we need to figure out the X values that would make it 0 because then it can't be those numbers. So the denominator cannot be 0. So if you solve for the denominator then, taking the 1 to the other side, X squared isn't allowed to be 1. Darby, if we take the square root here, X cannot be,
You can't do positive or negative.
yeah, +1 or -1. So when we're finding domain, we rely on the denominator and say, okay, it cannot be this number. How can I find that number that it can't be? By solving for the denominator. So if I think about a number line, here's -1, there's +1. It's not allowed to be those two numbers. But the domain can't be anything else. It's just not allowed to be those two values. So it's allowed to go to the left of -1, in between -1 and 1, and to the right of +1. Think about how we wrote that in chapter 1. So go back to chapter 1. How did we write that, Jeremy, when we're looking at domain? Good. Awesome. That's how we did domain. And these parentheses, because those parentheses are called intervals. So it shows where the graph moves from -infinity all the way to -1, in between -1 and 1, and then from +1 up to infinity. So when it cannot be a number, we put parentheses. That means that number isn't part of the answer. If I look at letter B is already a factor denominator. It says x minus 2 cubed. That can't equal 0. Your goal is to find the x in the denominator that makes it 0. Grant, what number would make this expression 0? 2. X cannot be 2. It doesn't matter that it's cubed. It's just saying that there are 3 quantities down there, and all 3 quantities represent x minus 2. None of those x's can be 2, but I'm not going to rate it 3 times because it's the same number. So grant if x can't be 2, our domain would be
-infinity
Yeah. That's it. So we're going to see if we can examine what's going on with a graph at these values and how the domain kind of matches with the special things in the graph. So in your calculator, if you can take that out and graph 1 over x. It says, what is the domain? Note the behavior around x equals 0. So just plug that in your calculator, draw yourself a little graph. This is the parent function of a rational function. It's the most basic rational function we would look at. Darby, how many pieces does this graph have?
That's 2.
2. Yeah, there's 2 parts. It has a part top right, and it has a part bottom left. Those guys are called branches. This actual graph is called a hyperbola. And it has 2 branches. And so those little curves are branches of my graph. 2 pieces, 2 branches. The name of it is a hyperbola. So instead of having a parabola or a polynomial curve, I got these branches, and that's called a hyperbola. So it says, what is the domain? Darby, what would the domain be moving from left to right?
Be negative infinity to 0, and then 0 to positive.
So it wants us to notice or note the behavior around x equals 0. X equals 0 is the y-axis. That's this right here. That's where x is equal to 0. That's a vertical line. It has this crazy little notation underneath. And it says, as x, remember that little arrow means approaches. It's really close to 0, and then there's a little minus sign after 0. That little minus sign means that 0 has a left side. So that notation, as x approaches 0 from the left. Numbers have a left side and a right side of them. So if you think of 0 being in the middle, I have numbers to the left of it, I have numbers to the right. And you have a number line. So as x approaches 0 from the left, what does f of x do? Or what does y do? F of x and y are interchangeable. So if I'm on the left side of the graph, and I'm approaching 0 from the left, so think about being in like a little car, and you're moving along the curve. From the left side, moving towards 0, closer and closer to 0. Where is the y going in the graph as you're getting closer to 0? So where is the y going? It's going down. What number would be going down to? Negative? Negative what? Infinity. Yeah, so it's going down to negative infinity. So as we're really close to 0, the graph is going down. On the other side, as x approaches 0 from the right, what does 0 do? Or what does f of x or y do, not 0? So again, you're in a little car, but now you're on the right side, and you're going in toward 0. Well, the y is going up, and it's going up to positive infinity. So those pieces are kind of doing opposites. They diverge. One goes down, the other one goes up at the value of 0. And that is our definition of a vertical asymptote, which we call the y. So a vertical asymptote is a line x equals a. In our case, it's the line x equals 0. That occurs when the y goes to infinity or negative infinity. So an asymptote happens when the graph goes to infinity or negative infinity because it cannot touch a specific number. That creates this boundary or wall in my graph. So it's saying the graph is going to get close to this wall and it's never going to touch the wall, but it's going to just kind of skim along the wall and move vertical forever. Or it's going to skim along the wall and go vertically down forever. That's an asymptote. An asymptote is found by setting the denominator equal to 0. The reason it occurs is because that's the number that x cannot be. I can't divide by 0. That creates this line in my graph that will never kind of happen in my graph or never exist in the graph. So that is an asymptote, a place where the graph does not exist. So think about it as like, I don't know, did you guys learn about the Berlin Wall? In history, maybe? Anybody in A-push? Nobody in A-push? You are, no? Yeah, not yet. So it's a wall that nobody can climb over. The graph cannot climb over it. Can't crawl under it. You can't pass through it. That's what an asymptote is. So find the vertical asymptote for y equals 1 over x minus 3. Well, I find an asymptote by setting the denominator equal to 0. A vertical asymptote is a vertical boundary line in the graph. So Evan, if I solve that little denominator there, the vertical asymptote is at x equals 3. So that means at the value of 3 in my graph, I have this kind of void. There's nothing going on there because at that number, that's where my denominator becomes 0. That's all an asymptote is. A vertical asymptote is a place that makes the graph undefined. So if I have a vertical asymptote, if I have a va, then I also have a horizontal asymptote, which we call the ha. So the va and the ha. The horizontal asymptote is pretty much the opposite of a vertical asymptote. It happens when my x value goes to infinity or my x value goes to negative infinity. And this is a line in y equals form because it's a horizontal line. So now I have this horizontal wall as well, this horizontal boundary. So if you look at the example here, we have 2x plus 1 over x plus 1. And it says, what is the vertical asymptote? Now, things to think about. This numerator is grouped together. The denominator is grouped together. I can't cancel out terms because they are grouped together. So they can't be separated, nothing can be canceled. If I want to find the vertical asymptote, I take the denominator and set it equal to 0. That's the process of finding the vertical asymptote. So Hannah, the vertical asymptote in this case would be at negative 1. So that means vertically at the number negative 1, I have this like void in the graph. There's nothing going on, but the graph goes up next to it or the graph goes down next to it. In your calculator, I want you to graph this, putting parentheses around the top, parentheses around the bottom. So you got to place parentheses around there to group it together. The calculator needs to know what's going on. And then I want you to trace the curve that is moving horizontal. Just hit the trace feature to see what is the horizontal asymptote. So you should see your graph going horizontally, kind of flattening out horizontally. What does it look like that number is getting closer to? That is our horizontal asymptote. And it should be like getting to be a decimal. And you probably can look at that decimal and say, it looks like it's going to be close to this number. Grant, what does it look like that graph is kind of tracing out to?
2.
Yeah, it looks like it's going closer and closer to the number 2. And you can do either side of the graph. That is a horizontal asymptote. So a vertical asymptote happens when the graph goes vertical, skims along a vertical line. A horizontal asymptote happens when it goes horizontal. So my graph is kind of like horizontally flattening out. And you can find that by tracing it. However, last year you discussed 3 little properties and little cheaters as to how to find a horizontal asymptote. And those are the 3 properties underneath. It all deals with the power. So we talk about these functions because we've been talking about degrees, the biggest power of our polynomial. So shortcut rules for finding the horizontal asymptote without relying on the calculator. Again, that's my big thing. How can we do it without a calculator? The first one says the degree of the numerator is equal to the degree of the denominator. Then the horizontal asymptote would be the coefficients in front of that degree. So, for example, if I have 3x squared, I don't know, we'll say minus 16, over x squared minus 4. And then is the degree of the numerator equal to the degree of the denominator? Yeah, I have an x squared, we have an x squared. That's the degree, that biggest power, they're the same. So then the horizontal asymptote would be the coefficients in front of that degree. And then what would the coefficients be in front of those powers on the top and the bottom? So what's in front of x squared? What's in front of the x squared?
Oh,
A 3. What's in front of the x squared in the denominator? A 1. The horizontal asymptote is found by taking those coefficients. When the powers are the same, the horizontal asymptote is the coefficients in front. So we're focusing on those powers being the same of that degree of the polynomial, the biggest power of the polynomial. That's the degree. When they're the same, the asymptote is the coefficients in front of that degree. That's called that leading coefficient. That's 1, shortcut number 1. Shortcut number 2 says if the degree of the numerator is less than the degree of the denominator. That means the power on the top has to be smaller than the power on the bottom. I'm going to use the same exact numbers, except I'm going to change my power. So I have 3x minus 16. I have x squared minus 4. Looking at the power on the top and the power on the bottom. Grant, is the degree of the numerator less than the degree of the denominator?
yes.
Yes, 1 is less than 2. So the horizontal asymptote then is at y equals 0. There is no calculation that you have to do. Because the power on the top is less than the power on the bottom, the horizontal asymptote is just at 0. And it's only one of the 3 choices. It's not all of them. So it's just looking at the powers and seeing which rule does it follow. The last rule flips it and says the degree of the numerator is greater than the degree of the denominator. So keeping my numbers the same, just switching my powers. Now the power on the top is 3x squared. The power on the bottom is just x to the first. If this happens, it says the horizontal asymptote does not exist. So when the power on the top is bigger, those numbers are going to continue to get large and larger and larger. And there is not going to be a horizontal asymptote. Because there's never going to be a number that kind of gives us that void in the graph. And that's because the numbers on the top are going to continue to be really, really large compared to the numbers on the bottom. So in over time, my fraction just gets bigger and bigger and bigger. It doesn't stop. Do you remember those 3 rules from last year? Maybe a little? No. This would have been the time when COVID was hitting. So we would have went over this in March last year. That might be a reason why it seems a little foggy, because it was around that time, chapter 8 was around March. So if you flip, we're going to look at an example. I think I've got 5 minutes, so we can go through an example here. And our goal is to kind of analyze this graph without using the graph. So we're really analyzing the function. The first thing is a vertical asymptote. And I'm going to just make a couple of notes here. So you have something to kind of think about. Set the denominator equal to 0. So the horizontal asymptote, or I'm sorry, the vertical asymptote is found by taking the denominator and setting it equal to 0 and solving for x. So if I take the 1 to the other side, divide by 2, my vertical asymptote is at -1 half. So that's the void in my graph, this vertical void, -1. Horizontal asymptote. I have to look at the powers. Anna, what's the power of the top and the bottom here? 1. Why is it 1? There's not more than one x, yeah. There's an x to the first, that's an x to the first. Remember, you're looking at the x's. So if I think about those 3 rules, Hannah, what can you say about those powers? They're the same. So the degree of the numerator is equal to the degree of the denominator. Anna, do you remember what that means then about our asymptote? So it's going to be the coefficient in front of that x divided by the coefficient in front of the x. There you go. So the coefficient in front of the x divided by the coefficient in front of the x. So we're not using the powers, but we're using the numbers in front of them. So the coefficient divided by the coefficient. Questions? I'm going to skip domain and range, but I'm going to go down a little further and find x-intercepts and y-intercepts. How do I find an x-intercept? How do you find an x value of a graph or a function? What number do you plug in?
You said y equals 0.
You set y equal to 0. So if you take your equation and set y equal to 0, I would have 0 equals 1 minus 5x, 1 plus 2x. If I solve for this and cross multiply, what happens when you take 0 times the denominator? Barbie, what happens when you take 0 times the denominator? It equals 0. So the denominator equals 0. If I take 0, or I'm sorry, my numerator times 1, I get 1 minus 5x. When you're finding an x-intercept, you're taking just the numerator, instead of just setting y equal to 0, you're setting the numerator equal to 0. So the denominator finds the vertical asymptote, the numerator finds the x-intercept. So I would take 1 to the other side, divide by 5, and I get 1/5. So denominator, asymptote, numerator, x-intercept. And then the last part here that we have to calculate is the y-intercept. See if you can find that by setting x equal to 0. Because I want to find y. And I'm out of time. Of course, it goes too fast. So you're really going to have to try and refer to this little skeleton that we just did. Yes, I wanted to go through another one, but I also thought it was important to go through some homework questions. That's why I only got through one example. But again, we're going to work more on this on Monday, more on it on Tuesday. So by then, we'll kind of have all those pieces kind of coming together. Have a fantastic weekend.
Thank you. Have a good day.
Thanks, you too, Jenny.
Uh,
You too. Later.
I have a question real quick.
Yeah, sure, Parker.
Where is the daily homework?